Okay, Mr. Remy Duquette has 20 years of experience building practical, effective solutions. He plays a key role in heading Maya HTT's industrial IoT and AI solution strategy and innovation. Today he will be talking about anomaly detection with generative adversarial networks, GANs, leveraging failure simulation data. Remy, please go ahead.
Yep, thank you. Yeah, it's on screen. Thank you very much, and it's an honor to be here today. Thank you for the very nice introduction, Mr. Gunter. So yeah, today I will speak about anomaly detection with generative adversarial networks. And without further ado, I will move on. I was introduced, so I'm not going to spend much more time here, but if you want to download a white paper, you can go back to my presentation and simply click on the link there. There's a nice white paper on the call for AI for engineers, and I think it touched on many points that we're going to be covering today. So machine learning, I think a lot of people sometimes get confused on what GANs are. So I just want to situate them with respect to the ecosystem of machine learning algorithms that we have available today to help augment our engineering tools and processes. So, you know, from let's say about 2012, there's been an exponential ramp up of the usage of these tools for various reasons. You know, we have access to a lot more data. We have a lot more compute power, GPU powered devices that we can leverage. So, but if we look at the progression, right, from supervised learning, where you can have labels on your data, so very simplistic kind of approach where a lot of people that can use these training and machine learning training in very efficient ways. Unsupervised learning, we just saw one example in the previous case with clustering and dimensionally reducing the model. So, you know, when you don't have any label in your data and you have big data, typically these methods are gaining, let's say, in accuracy and in the progress that they can make on the machine learning side. In a semi-supervised learning, you're kind of, you have a mix of some labeled data, some unlabeled data. So there's some interesting cases there. Reinforcement learning, especially in the control and engineering space, is very interesting to use. You know, rewards and functions. I presented that last time. I'll touch on this today in the last NAFEMS conference, but this is an interesting area for mostly on the control side of the engineering spectrum. And then today, I'll present a little interesting work on GANs and generative adversarial networks. And this is kind of a newer kid on the block, if you will, from a technology stack or algorithm stack perspective. So the first, the inaugural paper of that method was really in 2014. So it's only been, you know, 6-7 years now that this method was brought to bear. And I will provide a little bit of background here. So one thing I wanted to very quickly do is a level set, right? So in 2016, no one really in our domain were talking about AI and machine learning in general. So if you did look at the Gartner website back then, it was not even amongst the 100 top most searched terms in Gartner. By May 2017, it was all of a sudden ranked number 7. So it was kind of interesting to see what happened in that kind of time frame. So globally, something changed, and certainly in engineering, we started to talk a lot more about machine learning in engineering and AI in engineering. Don't like really the use of word AI because it's a little bit more convoluted now. But you know, in the end, it's machine learning, deep learning that we're talking about. One of the things that happened between 2012 and 2015 is all of a sudden human beings realized that if you process 14 million images and you can throw deep learning at it, all of a sudden it becomes better than human beings at recognizing things in an image and in a much faster way. So I think that kind of blew up our mind in terms of the potential and the possibilities there. In natural language processing, in a similar way, although it didn't, it didn't supersede human kind of capacity, it was still getting pretty close, right? With 6% roughly error rate on a any word counts that you would do on a paragraph or something. And but the algorithm could speak 100 languages. I don't know how many you guys speak, but I only speak three, and and one that I probably would fail on most tests. So in the end, it's important to recognize that there's been significant evolution in a very short period of time, and I think that's why we started paying attention. And then with some reinforcement learning, as we saw with DeepMind and Google's AlphaZero, it destroyed another software that was programmed by human beings. And this is really a big shift. And this is where I think we all started paying a lot more attention by seeing that let's say something in deep learning, in reinforcement learning domain, within 4 hours was able to learn in self-play mode to destroy another software that was programmed by human beings for over a decade. So I think, at least from my standpoint, that's when we realized that leveraging data and new deep learning architecture and technology is bringing a lot of power. So at the time, at NAFEM 2019, I presented a reinforcement learning kind of interesting approach to go from a full CFD model to a reinforcement learning agents and figure out the controls. Now today, really my focus is on the next step of the evolution, natural evolution of these types of techniques, and my key focus in the last couple of years has been on leveraging generative adversarial network for engineering purposes. And it kind of dawned on me, and you'll see it over the next few slides, that there is a key element of the training, that's the discriminator that we train to recognize, not to be fooled by a generator function that is generating fake data, or similar data as the original data, but not the real data. And the discriminator, really, if you train the discriminator super well on, let's say, normal data or normal simulation, right? When things are normal, then it kind of behooves that discriminator to figure out that if something goes awry, right? If something is an outlier, all of a sudden it's outside of the distribution of data that you gave it in the first place, it will recognize it as an outlier. And that's kind of the inception there of using GANs for outlier detection and anomaly detection. So for those of you who are not familiar with generative models, adversarial network models, essentially you have a generator function that's tried to learn to generate fake samples to fool the discriminator. And the discriminator function learns to distinguish, right, a real from a fake sample. And then the training is essentially in the loop of, going against each other in a zero-sum game, where you repeat until you reach a Nash equilibrium. So where about half of the time the generator fools the discriminator, and half the time the discriminator picks it up. So once you get to that point, then you have a pretty good equilibrium between the best generator and the best discriminator function. So if you look at a little pictorial, this is what it would look like in an environment where you have some data. In our case, whether it's 2D or 3D simulation data, and you have real simulation results, and then you have in a domain just the loads and boundary condition, and then you generate fake data from those loads and boundary conditions. You try and recognize, if it was a simulation result, so a 2D image or a 3D, field of results, that you would be able to know if it came from an actual solver with accurate patterns of the flow field or temperature field or structural whatever stresses that you're looking at. and then yeah, recognize if it's real or not. And in doing so, again, my focus has been on the discriminator aspect, because if you do not use failure data, which is a lot more expensive to generate, right? Let's be frank. Failure data in simulation is a lot more computationally expensive than when things are normal, right? When things are not failing. And so in this case, the discriminator is being kind of conditioned to learn to recognize those failure scenarios if you only throw a whole range of beautifully nice simulation that are not failure simulation. Then the generator can still be used, right, as a separate function for generating maybe initial conditions and speeding up your solver. So there's some other benefits to the generator function that is being trained in this loop, but it's perhaps not as powerful in terms of business value to the engineering community as the discriminator becomes. So I've looked at a lot of different implementations of GANs. There's many papers, and if you're interested, please contact me at the end. There's a whole list of different sources that I've leveraged in our work. But essentially, there's two big implementations. One is the original one, which is the minimax loss that was introduced in the original 2014 paper. And later on, there was some problems with some of uh, the weights that were set to a trivial function all the time. And so the generator would generate like very trivial things that the discriminator would, of course, realize or couldn't possibly realize it was, real or not. So you got to the zero-sum game very quickly, but it was not very relevant to the engineering problems that we were trying to solve. So there was then a loss, which is really the default in the TensorFlow GAN estimator that is being implemented if you use TensorFlow for your framework training. Is the better approach to use, or the better implementation to use, at least for our problem. So again, in our anomaly detection, we're mostly interested in the discriminator function that is being trained and created in this fashion. So why moving to Wassermann GANs or DC GANs for CAE? Well, a couple of reasons, right? As I mentioned earlier, simulation runtime is expensive and time consuming for these failure simulations. So capturing the normal distribution becomes very relevant and valuable. And then you can still use, and that's where the use of failure simulations become really interesting. You can validate that your critic or your discriminator function is working by passing it the actual failure simulation results and making sure that the discriminator recognizes this as an outlier and something different than the normal distribution. And in all cases, as you'll see, the results are showing that it does. So, from an outlier, picking up an outlier from the flow field or from a temperature distribution or something that goes awry, the discriminator is actually quite powerful in gaining that capability. So if you look at imagery, so you can think of in real-time operations, you can think of looking at a thermal imaging camera, for instance, right, to look at the thermal distribution or temperature distribution of a system. And if you've done a thermal simulation before, then again, by using the discriminator function to evaluate the distribution on the systems in real time, you can then pick out any anomalies or outliers that you would not otherwise have been able to pick out. And that even without running the failure simulation scenario. So the onset of failures and very early onset of failures are being picked out, because as soon as it starts deviating from the normal distribution, it picks it up and sends a signal, say, hey, something fake is going on here, because that's the terminology that's used in the GANs. But in the end, the fake bit means, there's an outlier coming out. So in terms of the convolution aspect of the GANs, there are some very specific tips and tricks that you must follow, and I've listed them here. I'm not going to go through them, but you can refer to those in your architecture for your convolutional neural network and the discriminator and generator functions and how you actually use them. So, outlier challenges, there are many different challenges. Most of the outliers are in what we call, relatively high dimensional space. The one kind of univariate outliers are nice, but really not that interesting to me. I'm more interested in the outlier when many things go awry together in sequence. So, we've picked up here a little bit of an app that leverages in the background those GANs functions, whether it's on telemetry data and simulation data combined, or imagery data, or, depending on what you have as a sensor type that you can then put in real production from your simulation result. So that's kind of the general, edge device type of architecture that you can put and move your ONNX model into an operational condition from your training of the GANs that was pre-trained on the simulation data, but used in real time for either from telemetry or imagery that is being selected. So it's very short today, but I wanted to finish this with Q&A.
Great. Thank you very much for the great presentation. Are there any questions? Maybe in the meantime, while you're typing in the chat box, I have one quick question. I was just wondering, can you give us an idea of the amount of data, the amount of simulations that needs to go into training a GAN successfully?
Yep. So in the end, for DC GAN specifically, so when you look at a cross-section of a result, either in 2D or from a cross-section from a 3D simulation result, it would take at very least about 500 simulation cuts to make it. So it's not as big data as other methods are needing, right? So if you look at reinforcement learning, you're looking at millions of samples to be able to properly control the system. In the case of GANs, it actually converges pretty quickly to the normal distribution of the system. So it doesn't need, as long as you cover enough of a design space from an input perspective to your models, it actually converges pretty quickly. So I would say 500 is the minimum kind of samples that you need, but it's not thousands of millions like other techniques in deep neural networks.
Thank you.
Which was another nice finding.
Then there's another question. Is only the detector being used for outlier detection? This seems like an autoencoder can also be used for the same purpose.
So autoencoders can be used for similar purposes for detection. They're not as generalizable though. So when you look at complete fields in 2D or 3D, autoencoders may be actually very difficult to train, and they may need a lot more input data. At least it's been our experience. So GANs has actually kind of been of interest because it generalized a lot better than autoencoders. And if you want to discuss offline, please contact me by email and we can have a longer discussion on that topic, because that's a topic that we can talk about for an hour.
Then there's one more quick question. Do you find training for time series data easier or more difficult than conventional applications? What architectures do you prefer for time series data?
For time series data, typically LSTM is my key go-to. So for long short and memory problems, so it captures the essence of the time series. Now there are simpler ways often to address time series with other techniques. So again, I've done a lot of work on outlier detection of time series with other techniques than just with GANs. Although I must say with GANs, again, the generalization, and if you give multiple, more than 10 real-time time series data into the GANs as an input, it generalizes a lot better as the dimension of the problem scales up. So as you get more and more inputs, let's say you have 22 inputs from your pump working in operations. Using a GANs work a lot better than other techniques, where other techniques will look at just a very small subset of inputs. So if you have less than 5 inputs, then don't use GANs. That's kind of there are better techniques in the low dimension spectrum for time series outlier detection. But for larger, higher dimension, GANs is actually a good way in combining it with LSTM as the deep neural network to learn the patterns is the way to go.
Mm-hmm. Remy, thank you again for your very great presentation. Let's move to the next speaker.